So what do these things mean here?
Those are the coefficients that go in
Okay.
front.
Great. So we would have 4
NH3.
NH3.
Okay, yeah. And then
And here it says gaseous. So what would we put after this?
a G.
Good. And then 7 O2 gaseous. And you want to leave a good space between these. Otherwise, it looks like 70.
Right.
Arrow. 4. And it says gaseous again. And then liquid H2O.
Okay. So plus 4 NO2G plus 8 or whatever coefficient 6H2O L.
Oh, it says liquid, so I need to cross that out and put liquid. Okay, now what do these coefficients mean? Here's a good way to understand any equation like this. The first thing that we're going to write here, though, is this. To the left of the arrow, these are called reactants. And to the right, what are they called?
Product.
That's right, products. And this actually gives us conversion factors. And the conversion factors is that you need 4 ammonia equals 7 O2 equals 4 NO2 equals 6 H2O. Now I know these are all different labels, but this basically says if you use 4 NH3, you need 7 O2 to react completely. Or if you want to make 4 NO2, you'd better have 7 O2 to start with. So do you understand what these, I call these equivalencies? Do you understand what they mean?
Yes.
But we don't use that.
We use the number of each element? Or
nope. I'm going to write this out and then I'm going to let you take a look at it. I know my left hand gets in the way. I've been working on a invisibility formula, but it hasn't worked yet. This is what we actually use.
Okay.
So how have I changed what I've written?
You just added the mole unit.
Yeah, I added mole. So this says if you wanted to use exactly 7 mole of O2, you would need exactly 4 mole of NH3. And these numbers, the 4, the 1, the 4, and the 6, because they represent these, and these above are counted, that means that these numbers here are also counted for all practical purposes. And they have an infinite number of significant figures. Okay?
Okay.
So that is essential for the rest of the semester that you understand this part right here. For example, I'm going to slide this up. If I asked you how many moles of NO2 can be made by the complete reaction of 21 moles of O2, how would we solve this? And the answer is you would start off with 21 moles of O2, and we would multiply by moles of NO2 over moles of O2. So where do we get this ratio?
From our equivalencies.
Right here. So I'm going to put 7 with O2. I'm going to put 4 with O2. And now you can see why I picked 21.
Right.
7 will go into 21 3 times, and 3 times 4 is 12. And because this has 2 significant figures, this should have 2 significant figures. So that's why it's important to know this. Okay? Let's do another one here. Okay, the equation for the reaction of aluminum So for this one, it's just like the other one. I'm not going to write out the equation, but they say if you use 6.0 times 10 to the 23rd molecules of Br2, and we want to get to how many atoms of aluminum, we can actually use these coefficients here, and we don't have to use moles. We can use atoms or molecules. So we could do this. Now, why do they call the aluminum atoms, and why do they call the Br2 molecules?
They're diatomic.
Pardon me?
They're diatomic.
A little louder?
They're diatomic bromine?
Yeah, because there's two atoms in there, which means it's a molecule, not just an atom. Okay, so where do we get this ratio of molecules to atoms? Right here. 3 molecules to 2 atoms. Now 3 goes into 6 2 times, right? And 2 times 2 is 4.
Right.
So this is the one way to use it. We can use these as atoms or molecules, individual units, if you will, or we could do moles. Okay?
Okay.
Okay, a 0.2 gram sample or mole sample of magnesium burns in air to form 0.2 mole of solid MgO. What amount of oxygen is required for the complete reaction? So for this one, you have to make an assumption. If you have magnesium and it's burning in air and it's making magnesium oxide, and that's a solid, and this is also a solid because all metals are solid at room temperature, save one, which is mercury. What does this have to be reacting with to make this? And the answer is, well, this has oxygen in it. There's no oxygen over here, so we need to have oxygen over here. So what is magnesium likely to react with that's in air that has oxygen in it?
Just O2?
O2. That makes perfect sense. And why would we not use something like CO2, which is also in air?
I'm not sure.
Well, because it has carbon in it, and we don't really have carbon in any of the products.
Oh, okay. Yeah.
Does that make sense?
Mhm.
So a lot of the questions I ask you are really kind of questions to nudge you into thinking about these things in a chemical fashion, you know, almost like a, oh gosh, of course, fashion. Does that make any sense? So
Yeah.
when I ask you why not CO2, it's hard to fathom what the answer is. But then when you start thinking about, well, if it's on this side, it's got to be on that side.
Right. It's just not in the products.
Right, right. So, you know, these are fundamental questions that oftentimes we ask in class to get students used to thinking about those things. Okay, now if we start off with 0.20 mole and they form 0.20 mole here, what amount of moles in O2 is required? Now this is not balanced. So this is the first problem where we have to balance. And when you balance, you only have 2 rules. Rule 1, it's okay to change coefficients. A coefficient is the number in front of the formula. And it's not okay to change the formula. 2 rules, a do and a don't, if you will. Do, don't. So with this example here, I'm going to rewrite it, and I'm going to do a do and I'm going to do a don't. I'm going to start with the don't. So we have magnesium solid reacting with O2 gas, making MgO solid. So are you ready for the don't?
Yeah.
Do you see the don't?
Yeah.
So I changed the formula.
Right. You just want to put coefficients, not the subscript.
So let's look at the do. Here we have one magnesium and here we have one magnesium, so that's good. Here we have two oxygens, but only one. So we're going to change the coefficient in front of the magnesium oxide here to a 2.
Oh, and then put a 2 in front of the magnesium in the reactants.
Correct. So this is okay. That coefficient means that. But we don't write out 2 of these. We just say, hey, 2. And then we're going to put a 2 in front of the magnesium, just as you said. Okay, so that's all there is to changing that. And remember, the question was how many moles of O2? So we have 0.20 moles of magnesium times moles of O2 over moles of magnesium. So where do we get these numbers from?
From the balanced equation?
Right, and that is this right here. So what are we going to put with magnesium?
2 moles magnesium.
Okay, and oxygen?
1 mole.
1. The default coefficient is 1. So we can see we don't even need a calculator for this. We have 0.10 mole of O2. Fair enough?
Yeah.
So if a problem like this were asked on an exam, this is what I would expect to see. The balanced reaction and then the calculation below. And notice how I have labels in the calculation below. What does this look like without labels? It looks like this. So up here, do we have any explanation for why the moles at the beginning are different than the moles at the end, that they represent different compounds?
No.
No. And what is this 1 mole to 2 mole? It sounds like a ripoff. I'm getting 1 mole for every 2 mole. What kind of world is that? Right?
Right.
No, that's the kind of world I want to live in where I'm getting the 2 moles. But, labels here make everything so much more clear. Agreed?
Right.
So we want to make sure we label things like that when we're working with this. Okay, so let's practice balancing equations. Production of ammonia by combining N2 and H2. So notice we have the labels here. So when we say production of ammonia, is ammonia a reactant or a product?
A product.
Right, because production means you're making it. And when you combine these two, it sounds like you're reacting these two, right?
Right. Those are.
So there are different words for reacting. It could be combining, putting together, whatever you want.
Okay.
So what do you want to change first here?
Well, I would put a 2 in front of ammonia.
So would I.
And then I'd need to put a 3 in front of H2.
And there you go. Done. How about B? B is going to be a little harder. And whenever you are reacting a compound instead of just elements, it always makes it harder to balance.
Right.
In addition, this is harder to balance because we have to keep track of hydrogens here and over here. Okay, so what do you want to do first?
Well, there's 3 hydrogens on the products and 2.
There are 4 hydrogens on the product side.
Oh, I wrote it down wrong.
Okay,
Shouldn't. Okay.
so you must have written CH2OH.
I wrote CH3OH. Oh, yeah, I wrote CH2. I just changed it to CH2.
Okay, so we need
So I
4
put
over here.
in front of the H2.
Okay, excellent. How many carbons?
1. And then 1, and then 1 oxygen. So
Okay, so we're done. So we got through that one pretty easily. The production of sulfuric acid. So the way to figure out what the formula of sulfuric acid is to start with the sulfate ion. And to get sulfuric acid, you add 2 hydrogens, and that's sulfuric acid. And the reason I know it's 2 hydrogens is because of that charge of 2.
right.
So this is what we're going to make. And notice here, they don't say anything about the state, so we're not going to worry about that. Now it says we're going to combine sulfur, oxygen, and water. So sulfur, oxygen, and water. Water we know is H2O. Now one of the problems here is this oxygen. When you take oxygen off of the shelf in a bottle, do they come in single atoms or do they come in pairs?
They're diatomic.
So we want to write an O2 there. The diatomics are Honkelbrief, hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine, Honkelbrief. So now we're ready to balance. I usually, when I balance these things, I just start on the left and go to the right. So sulfur is good, right?
Right.
Oxygen,
Need a 2 in front of it.
we want to put a 2 in front of that, but if we put a 2 in front of that, what about that one?
Oh, yeah, we have 3 of them over here and 4.
Yeah, so now I think, okay, I don't want to mess with that right now. So I'm going to go to hydrogen instead. How many hydrogens here?
2.
How many here?
2.
2, right?
Right.
So now I got to suck it up, so to speak, and I got to deal with the oxygen. Now, this is a clever way to think about it. How many oxygens do we have over here?
5. Oh, sorry, 4.
4. How many oxygens do we have here?
3.
3, right? But we want 4. Is there any way to get 4 oxygens over here without messing with the hydrogens, because the hydrogens already match? Well, we can make a little game of it. So here's the game. Here, we get 2 oxygens for every one of these, right? So I'm going to call this coefficient X, and I'm going to call this Y. Fair enough?
Okay.
Wouldn't we say that X times 2 plus Y times 1 is equal to the number of oxygens?
Okay.
Okay, so we don't want to change Y. We want to keep that 1. So X times 2 plus 1 times 1 is equal to 4. We want 4. Are you with me here?
Yeah.
So X times 2 is equal to 3. X is equal to 3/2.
Okay.
So let's try that. We're going to keep this as a 1, and this is going to be a 3/2. Now, when you see a balanced reaction with a fraction in the coefficient, you don't like it. But remember, this means 1 to 3/2 to 1 to 1. And they're just ratios. How can I get rid of that 3/2, but also keep the ratios the same? And the answer is double everything. If I double 1, what do I get?
2.
And if I double 3/2, what do I get?
3.
3.
Mm-hmm.
So let's try that. I'm going to write this down here below. 2 sulfur plus 3 O2 plus an H2O gives us, and that should be 2 H2Os, gives us 2 H2SO4. And what I'm going to do here is I'm going to make a little list. And we're going to count. How many sulfurs on the left?
2.
How many oxygens on the left?
8.
Good. How many hydrogens?
4.
Okay. How many sulfurs on the right?
1. Oh, 2. Because
2.
coefficient.
How many oxygens on the right?
8.
And how many hydrogens on the right?
4.
Okay, so do our lists match?
They do. Yeah, I think that's the confusing part for me. Maybe if you could go over the formula used with the x and the y one more time, with the
Well,
3 halves multiplying by a fraction.
all I did here was I substituted variables for the coefficients.
Right.
So I said, let's let this one be x, let's let this one be y. Okay. And then I also wanted to make sure that I would get 4. So that's why this ended up being 4. But I also didn't want y to change from 1. So I made that a 1.
Oh, okay, okay.
Okay.
Right. The number you multiply the variable by is the number of oxygens.
Yeah, the number of O2. So here, if we have this formula, x times 2 plus 1 is equal to 4, and I take 1 times 1 and bring it to the other side, I get 3. Does that make sense?
Yeah.
And then just divide each side by 2.
Yeah,
So this is something that's usually easier to do this way. Another way to do it is brute force. So here's what I mean by brute force. So this is what we had to begin with, right? Sulfurs match, hydrogens match, oxygens do not. Correct? So how do we get oxygens to match? We put a 2 here, and what do we have?
Then we have 4H2.
Now we have 4H2, which means we got to put another 2 here, right? So now we have 4H2, but now we have 2 sulfurs. We're not going to worry about that till later. So we have 4 hydrogens. How many oxygens on the product side?
8.
How many on the reactant side?
4.
How can we get 4 more oxygens without changing the number of hydrogens?
Just put it on the O2.
So what do we want to put here so that we have 8 oxygens total?
2.
Okay, let's try it. What's 2 times 2?
It's only 4.
And what's 2 times 1?
2.
What's 4 plus 2?
Not 8.
Okay, that didn't work. So if you're not going to use 2, what are you going to try next? You're going to try 3.
All right.
What's 3 times 2?
6.
2 times 1.
7. So that makes sense.
That makes sense. Okay, so you can try any number you want in front here and see if it works. Now, why did I change the number in front of O2 instead of the number in front of H2O? And the answer is I knew if I changed this number, I'd have to go back and mess with hydrogens again.
Right.
Okay, that's why having compounds in the reactants make it tougher. If you change the coefficient in front of a compound, you have to then think about all of the other elements in that compound. And I left sulfur for last. And the reason I did that is because now that I see this doesn't change, I have 2 sulfurs. So what do I put here?
A 2.
Now, when I put the 2 there, does that change the number of oxygens?
No.
Does that change the number of hydrogens? No, right?
Right, it doesn't.
So if it doesn't change any of those, and I know the other ones are already balanced, I don't need to mess with any more coefficients.
Right.
So you like to leave pure elements for the last. Okay, so this is what I call brute force. And, either way gets you the same answer. Fair enough?
Okay.
Okay, what about this one here? Balance the following.
I would put a 2 in front of the products
Okay,
and a 3 in front of chlorine on the reactants, and then a 2 in front of, yeah,
chromium.
chromium.
Precisely. And the way to think about this one is here you have 2 chlorines and here you have 3 chlorines. And you know that you're going to have the same number of chlorines. So just multiply 3 times 2, that's 6.
Yeah.
And say, well, I want 6 chlorines. How do I get 6 chlorines? You put a 3 in front of that. Here you put a 2 in front of that. And then when you put the 2 here, you got to put the 2 there. And you leave the chromium for last. Because when you put the 2 there, you don't change anything else. Does that make sense?
Right.
Okay, what about here?
Well,
Which one are you going to leave for last, or which ones?
I guess carbon.
Carbon and silicon, if you can, right?
Yeah.
Okay.
I would put a 2 in front of, yeah, CO,
Right.
but then I'd have to put a 2 in front of C, and then I think carbon, and then we'd be done.
Then you'd be done. There you go. And so here, in this case, we left the carbon for last, and we didn't have to mess with the silicon. How about this bottom one? You probably want to leave iron for last, correct?
Right.
So let's mess with H2O. How does that look?
Well, the hydrogen is fine.
Spot on.
The oxygen needs to be doubled, so put a 2 in front of H2O and then a 2 in front
Hang on. Doubled?
O4, and then it needs to be quadrupled.
Yes, there you go. So I think for a moment you were thinking this 2 belonged with that oxygen.
Right.
And it does not. Okay. So what is the default subscript if it's not written? It's a 1.
Okay.
So we need 4 of these guys. And now we do have the correct number of oxygens. And notice we kind of left hydrogen for last. And look at this. We have 8 hydrogens. And how many do we have here?
Just 2, so multiply by 4.
Okay, now when we put that 4 in front of the H2, do we need to worry about the number of ions changing or the number of oxygens changing?
No.
No. So that's the beautiful thing about leaving pure things for last, is that when you change the coefficient in front of there to match the other side, you're done, so to speak. So how many ions do we need?
3.
And there you go. And we can double check this, right? How many ions on the left?
3.
How many hydrogens?
8.
How many oxygens?
4.
Now this is a don't. So how many ions?
3.
How many oxygens?
4.
How many hydrogens?
8.
384, 348. Do these lists match?
Mhm. I mean, they're in different orders.
They do match, but they're in different orders, which means this is a don't. We don't need to make the list match how the atoms appear, do we?
Okay.
Can't we do this and make the list the same as this list in the same order?
Yeah.
Yeah. So here we get 3, here we get 8, here we get 4. Do the lists match?
Yes.
384, 384, they match. And they're much easier to compare when you make the list in the same order. Okay. So here we have some more balancing, but I think you're going to get the hang of this, so we're going to skip the balancing, okay?
Okay.
Okay, identify each of the following statements as true or false. So they're talking about reactions at equilibrium. So reactions at equilibrium are reactions like this. This is actually a compound called acetic acid. And it reacts and gives you this and this. Okay. This reaction does not, however, go to completion. Meaning if you start with 10 of these, and you don't get 10 of these, what happens is some of these recombine to make that. So the reaction happens both ways. This is called an equilibrium reaction when you have these arrows that go both ways. Sometimes the arrows are written like this. So whenever you see that, it's an equilibrium reaction. And at equilibrium, so when the reaction is at equilibrium, the forward rate of reaction is the reverse rate. So that means if one of these is coming apart, two of these are coming together. That's the same rate. If 100 of these are coming apart, 100 of these and 100 of these are coming together. So do you kind of understand that rate idea?
Yeah.
Okay. And the amount of these does not have to be the same. It's not going to be like you have 100, 100, 100. In this reaction, you have about 100,000 of these, and you have about one of these and one of these as a ratio. So out of these 100,000, if one of them comes apart, these two come back together.
Okay.
Same rate. Okay. So the concentration, we say, of reactants and products do not have to match. In fact, they usually don't match. They're quite different. And we say if the concentration of products is greater than the reactants, we call it product favored. Does that make sense to you?
Is it like the number of molecules?
That's right. So concentration would be akin to the number of molecules. So if the number of molecules of products is greater than the number of molecules of reactants, it's product favored. Does that make sense? And if the reverse is true, if the concentration of reactants is greater than products, we call it reactant favored.
And you can determine that based on the at the top of the page, how you have different numbers equaling.
These are never given. So that's determined by something called an equilibrium constant. And I'm not sure if our chapter talks about it, but let's go ahead and talk about it.
It doesn't, I don't think. I was wondering about that with product favored reactions and reactant favored reactions. There was this like crazy formula I found online that I didn't understand.
Equilibrium constant is given the symbol K, and K is equal to products over reactants. So in the above, it would be the product times the product over the reactant. And so you see, this means concentration or number of molecules, if you will, okay? So the number of molecules of this times the number of molecules of that divided by the number of molecules of that. So do you kind of understand this formula here?
Yeah.
Okay, so imagine it's product favored. Are you going to have a lot of the top or a lot of the bottom?
If it's product favored, you're gonna have a lot of the top.
Okay, so product favored, K is going to be greater than 1 because you have a whole lot of stuff on top and not much on the bottom.
Right.
Now, what if you have reactant favored? Are you going to have a whole lot of this stuff or a whole lot of the stuff on the right?
You're gonna have a whole lot of the denominator.
Denominator. So if that number is big, what's K going to be?
Less than 1.
Right. And that's how you use K. If it's bigger than 1, it's product favored. If it's less than 1, it's reactant favored.
And
And K is something that you need to be given.
okay.
No one memorizes Ks.
And we aren't given those numbers.
Some crazy people memorize Ks, but I don't.
So if we're asked, like, what is it, product or reactant favored, how would we know how to answer the question without using this formula?
You wouldn't.
Okay.
Except for we can say this, and this is in the chapter. Acids. Acids basically do this. So what do these two acids have in common? And the answer is they make H pluses. Do you see that?
Yeah.
So if they make an H plus, what remains is whatever's left over when you take away one hydrogen. But whatever's left over also has to have a negative charge so that that negative charge and that plus equals 0, which is the charge on this. So do you see why this has a -1 sign here?
Yeah.
And do you see why it has 2 hydrogens?
Yes, I do.
Okay, this is also an acid. So what's it going to produce? H plus. That's what acids do.
Oh yeah.
Okay, so what's left over if I take away an H plus? 1 hydrogen, PO4, and the charge on this has to be the right charge. So when I add it to +1, it comes out to be -1. So what's the charge on that?
Well, phosphate's 3-.
Right, but here, all we have to do is look at this. The charge on this plus the charge on this has to equal -1.
2-.
Right. And this is also an acid. So what's it going to make?
H plus.
What else?
And just PO4 3-.
That's right. And notice that the charge here and the charge here adds up to -2. So what type of acids are these and what type of acid is this? This is a strong acid and this is a weak acid. And this one is governed by equilibrium. How do I know, based on what I've written here, that these are equilibrium reactions?
Just the arrows.
That's right. How do I know this one's not?
And it just has products going to reactants.
Right. So strong acids, you make only products and you have basically no reactants left. What's the K going to be here? I'm not asking for a number. I'm asking for relative to 1.
Okay, wait. So I would say that it's product favored
Correct.
just because it separates.
Yeah, because it's a one-way arrow.
Yeah.
So what's K going to be? Really big or really small?
I mean, it's going to be over 1.
Yeah. And it turns out to be it's much greater than 1. In fact, it's like infinity.
Okay.
Okay, what's K going to be here?
Less than 1.
Less than 1. And actually, this one, we would say might be less than 1. This one's much less than 1. This one's much, much, much less than 1. Meaning that taking the first hydrogen ion off of this thing is easier than taking the second one. The second one is easier than the third one. Okay?
Okay.
So let's see if we have enough to answer this. Identify the following statements as true or false. All chemical reactions are product favored at equilibrium. Well, are they?
No.
No. There is no observable change in a chemical system at equilibrium. And the answer is true because the concentrations don't change.
It's because of the rate goes both
Yeah.
ways.
So the number of reactant molecules stays the same. The number of product molecules stays the same at equilibrium, even though reactions are still happening. So you don't really have an observable change. It'd be basically like, imagine you run into a millionaire, okay? You give him $1 or her $1, and she gives you $1. Is there any observable change in the amount of money either of you has?
No.
No. So that's equilibrium. But imagine, on the other hand, for every $1 you give the millionaire, they give you $2. Will there be an observable change in the amount of money each of you has?
Yes.
Yes, definitely. It'll be easier to see that you're getting money probably than they're losing money, unless you're a millionaire, and I'm not. I know one. I know a millionaire though.
It's exciting.
Yeah, it doesn't help me though. Actually, I know 2 millionaires now. I'm not part of the club. I don't worry about it. Okay, so there's no observable change. In equilibrium involving a weak acid and water is product favored. Well, what have I told you about weak acids? K is much less than 1. So what does that mean? Product or reactant favored?
Reactant?
Reactant favored. Weak acids are reactant favored. That means that weak acids do not like to give up a hydrogen.
Okay.
So, maybe the way to think about this guy is not stingy with his H pluses, and these guys are stingy with them. They don't want to give them up.
Okay.
Fair enough? And stingy may be the wrong word. Maybe these guys are more protective of their hydrogens, and these guys just don't care about their hydrogens. I don't want to use the wrong analogy to offend anyone. So maybe we could say they're too stingy, or we could say that they're too protective. I don't know. Fair enough?
Yep.
Okay. Okay, refer to the book. We're skipping those. Name and give the formulas of 2 acids that are strong electrolytes. So a strong acid is also called a strong electrolyte. And a weak acid is called what type of electrolyte?
Base?
What's that?
Well, a weak electrolyte.
A weak, that's exactly it.
Okay.
So these words are synonymous. And the reason we have this word electrolyte is if you have a whole bunch of ions in solution and you put a light bulb in here, so this is supposed to be my light bulb, and you put electricity through this light bulb, and it has to travel through the solution to get to the light bulb, this light bulb will light up. Okay.
Right.
The more ions you have, the stronger the light bulb lights up. So if you do this with a weak electrolyte, and you put your light bulb in here, here's what your light bulb does. So do you see I have only 3 lines here instead of a bunch?
Mm-hmm.
That means it doesn't light up very well. So weak electrolytes conduct electricity weakly, and strong electrolytes conduct electricity strongly. And that's the origin of the term strong electrolyte and weak electrolyte. how well it conducts electricity through water. Because water, it turns out, is a really weak electrolyte.
So,
And you might wonder, well, why am I supposed to get out of the pool when there's a thunderstorm, or not be in water when there's a thunderstorm?
right.
And the answer is that two reasons. If lightning strikes near you, the voltage is strong enough to course through a weak electrolyte. So the voltage will make the electricity flow because the voltage is so great. Okay. But also, what's the likelihood that you're standing in pure water and not water with dissolved ions in it? Well, think about the ocean.
Oh,
The ocean is salty water. There's a lot of electrolytes in there, right?
possible to find that.
Yeah. So if you are in the ocean and lightning strikes near you, you're probably going to die. And if you're in a swimming pool, guess what they use to clean the swimming pool and to keep it from keep bacteria from growing?
They use chlorine.
They use chlorine, and basically it's not pure chlorine, but it's an electrolyte.
Uh-huh.
So your pool has electrolytes, not as much as the ocean, but it's a conductor.
Well,
In
could you say
fact,
that any salt then would be an electrolyte?
any salt that dissolves.
Okay.
Some salts don't dissolve.
So it's basically just the ionic um,
Yep.
compounds in the compound separated in the water.
And if you take a look here, do you see how strong acids make ions?
Right.
A lot of them, right?
Mm-hmm.
And you see how weak acids make ions, but not many?
Right.
Okay, so acids are electrolytes. Strong acids are strong electrolytes. Weak acids are weak electrolytes. And here they want to know what are some strong electrolytes and what are some weak electrolytes. So I'm going to give you some strong acids. This one here. This one here. This one here. These are all strong. And here are some weak acids. H3PO4. And see, this is interesting. This has more hydrogens than any of these I've listed, doesn't it?
Right.
Does the number of hydrogens tell you whether you're strong or weak?
No.
No, not at all. This is a weak acid.
The number of hydrogens is just to balance the charge, right?
Yeah. Here, this is the only one that comes off, though. These three do not.
Okay.
So this is a weird one. H2CO3. These are weak electrolytes. Also, here are some more weak electrolytes. H2PO4 -1, HPO4 -2. These are weak electrolytes. So here for this formula here, if this one's weak, the other ones are even weaker. So that means that this is also a weak electrolyte. So how am I getting these other formulas? I'm taking away one hydrogen and making it more negative. So these are some examples of strong acids and weak acids. And for bases, bases are usually going to have this formula. And these are strong bases. And the reason these are strong bases is that when you put them in water, they dissolve. And the reason they dissolve in all these cases is because if you have a group 1A ion in your formula of your compound, it will dissolve in water. So here, when this dissolves in water, if I write it out like this, you can see the ions right there. And here I've introduced a new term, AQ. Do you know what AQ means?
Aqueous.
Right. And what does aqueous mean?
Um, just water in water.
Dissolved in water.
Dissolved in water.
Not just water, dissolved in water. So if you take a rock that's a solid and you put it in water, does the rock dissolve?
No, you just got H2O plus the rock still.
Yeah, it's still a rock that's a solid. So it's a wet rock, but it's not dissolved. So here, aqueous means dissolved in water, which means it's separated into its ions if it's an ionic compound. So these are some strong bases, and there's only one weak base that you need to memorize, and that's this, ammonia.
Okay.
So in answer to this question, give the formulas of two acids that are strong electrolytes. Any one of these. Weak electrolytes, this is also a weak electrolyte. So how did I get this guy from here?
You just took away a hydrogen and added
Yeah.
a negative charge.
So the deal is, if you have a strong acid that can give away more than one proton, once it gives away that first proton, it then becomes a weak acid forever. Okay.
What about then? So the only one I see that has two hydrogens that I wrote down for strong acids is sulfuric acid. Then where else would we see that?
Would you see what?
The H2 to get rid of the one, if it has one extra H to get rid of.
Right here, H2CO3.
And then it just becomes the weaker acid.
Yeah, so this is weak and it becomes weaker.
Okay. But if
Yeah.
it starts out as strong and it has two, then it becomes weak.
Right. There are no strong acids where all of their H's are strong. None of them.
Okay.
So with strong acids, only the first one will be the strong H. The rest will be weak. If there are more than one, like this.
Okay.
Okay. So here, give the formulas, name and give formulas of two bases that are strong electrolytes and one that is a weak electrolyte. So let's name these things. What do you call this guy? Call it nitric acid. And it's based on this being what looks like a nitrate ion. And so you get nitric acid. This is hydrochloric acid. This one looks like the sulfate ion, right?
Right.
So sulfuric acid. Now, what do you call this guy? You call it hydrogen sulfide, hydrogen sulfate. So you name it just like you would name the ion. How do we name this one? What would your guess be? It looks like a carbonate ion. So what type of acid would that be?
Like hydrocarbonic acid or
Well,
something?
take a look here. When there's an oxygen, do we use hydro in front of it?
No, so just carbonic maybe then?
That's precisely correct. And we call this two things, hydrogen carbonate, but we also call it bicarbonate. What do we call this one? Acetic acid. So this is one that looks like the acetate ion.
Right.
If I cover that up, looks like the acetate ion. So the acid, it's not acetate, it's acetic acid. You find this in a vinegar.
Right.
And what would this one be called? Not phosphate, but phosphoric. And this one would be dihydrogen phosphate and hydrogen phosphate.
Okay.
Now you name these just like you name ionic compounds. So you name the cation first, lithium, then the anion second, hydroxide, lithium hydroxide.
Mm-hmm.
What would this one be called?
Sodium hydroxide.
Correct. How about this one?
Potassium hydroxide.
Correct. And this one is ammonia, not to be confused with ammonium.
Right.
And turns out ammonium is a weak acid.
Okay.
Because it can do this. There's that H plus. Okay.
Mhm.
So we have accomplished this task. Okay, now here, this pertains to the lab that I posted yesterday about precipitation. So you're supposed to decide which of the following are soluble in water. And you want to familiarize yourself with the solubility guidelines that are in your book. And they're probably near page 140 or something like that. Let's see. 134. So here are the solubility guidelines right here. So this is used for, I'm going to zoom in on this just a little bit and we'll look at some of this, but we won't be able to look at this and the problem simultaneously.
That's okay. I have it written down.
Okay, so these are the things that are soluble. So notice that sodium, potassium, ammonium, if you have an ionic compound with one of these three things in there, it's going to dissolve. If it's got acetate ion, nitrate ion, chlorate, or perchlorate. Now, the rules I gave you in my handout were basically group 1A ions, ammonium, nitrate, and acetate. And the reason for that is because we don't run into many chlorates or perchlorates. Now, notice here, I think you mentioned this yesterday, that mercury 1 was an exception.
Right, but you said,
And
well, we won't be using it.
I didn't list that because it's not that important.
Okay.
Now, here, salts containing F minus, I don't know if I put this one down. I may have that. If you take a look at these two, they're very similar, agreed? Sulfate and fluorine. Exceptions are silver, lead, barium, strontium. The only two that don't match are magnesium and calcium.
Looks like calcium in there too.
Oh, I'm sorry. Calcium is there. The only thing that doesn't match is magnesium.
Okay.
Magnesium sulfate is soluble. It's got a common name called Epsom salts. You ever heard of that?
Mm-mm.
People use it to soak their feet in. It's supposed to help alleviate, sore feet.
That's good for your muscles.
Okay, so magnesium sulfate is soluble, but you can see that if you leave magnesium off of this, you could keep the exceptions for both of these the same.
Right, that makes it easier to memorize.
Yeah, and silver, I would actually say that silver fluoride is probably not very soluble. Okay, so, and then here they have insoluble salts. I don't usually give this, and the reason is simply this. If it's not here, it's not soluble.
Right.
So here, is there anything here about carbonates? No, it's not soluble. Is there anything here about phosphates? No, it's not soluble. Is there anything here about chromates? No, it's not soluble. How about sulfides? No, it's not soluble. Now, there are exceptions, of course. If you combine sodium with the carbonate, it will dissolve. So this is the rule you want to know most of all. These are the things that usually do dissolve. And then you have to understand the exceptions to know if any of these will dissolve, any of the not solubles. Okay, so you have the rules written down. Let's take a look at some of these. So, which are soluble in water? So for A, it's going to be,
zoom out a little bit.
pardon me? Oh, I need to zoom out. Yeah. So for A, it's going to be barium nitrate because nitrates are always soluble.
Okay.
Sulfates are usually soluble, but there's an exception that says barium sulfate is not.
So it's basically calcium. What I wrote down for sulfates, or are we talking about nitrates? No, sulfates. It says that if it's combined with calcium, strontium, barium, lead, or silver.
Right. Then it will not dissolve. So that will not dissolve. It's not soluble.
Okay.
And the same with barium carbonate. There's no rule that governs barium and carbonate. So you say not soluble. And here, since we're only writing down the ones that are soluble, it's this one. And this one's soluble because of the nitrate ion.
So anything with a nitrate's soluble.
Anything.
Same with acetate.
Yeah, anything with acetate. So take a look here. That's got acetate. That's soluble. It's also got sodium, which makes it doubly soluble, right?
Right.
This one has sodium. It's soluble. Oh, that one has sodium. It's soluble. So you see, anything with sodium, you say, hey, that'll dissolve.
Even if it has a sulfide and it's not in that exception.
Doesn't matter.
Okay.
Sodium is one of those things that makes anything soluble.
So is that with all the 1A ions will make it soluble?
Yep. So how about C? We have a rule for bromine. Bromides are soluble unless combined with what?
Silver, lead, or mercury 1.
So this one's not soluble. How about this one? Are we going to focus on the K or the Br?
Okay.
The K, because it's in group 1A, it's soluble. So here we've got Br negative, right?
Right.
And we've got aluminum +3. So this one should be soluble because it has Br in it. Now this one, there's a few things that should strike you as weird. If this is an ionic compound, why isn't the formula this? Because aren't ionic compounds supposed to be the simplest formula?
Right.
So why isn't it this? Turns out this is not ionic. It's a molecule. So this is the molecular formula and not the empirical formula. So this one I'd also take with, I don't know, it's molecular. Because the fact is, you don't know, it's molecular. And our solubility guidelines are not based on molecules, they're based on ionic compounds.
Okay.
Okay. So I wanted to address that formula being weird. How about this one? Which of the following compounds are water soluble? And what are the ions?
Well, I think A is water soluble because of potassium.
Okay, so what are the ions?
K plus.
Uh-huh. And?
Plus I minus.
That's right. How about B?
Well, it's an acetate, so yes.
Absolutely. What are the ions?
Magnesium 2 plus.
Okay.
And 2 minus.
Nope.
Oh, well, it would be minus and then a minus, right? You need to add 2 of them.
And 2 of them.
Okay.
Okay, how about C?
Well, it has a phosphate, but it shouldn't matter, right? Because of
potassium wins.
Okay, so it's soluble too.
So
and then
2 potassiums, right?
2K plus. And
now,
then,
should I write out the following this way, or should I write it out this way? Which way should we do it?
Well, it's just one hydrogen. So wouldn't it keep it? Wouldn't it?
Well, the fact of the matter is that this is weak, right?
Okay.
This is weaker. And this is weakest. So what does weak mean? Weak means it doesn't like to give up its hydrogen. Oh, this is supposed to be a... So weak means it doesn't like to give up the hydrogen. And here, when I write it this way, it's given up the hydrogen.
It should then be HPO4.
Right, and it should be a -2 because you have plus 2 over here. How about D?
Yes, because of 1A ion.
What's the other ion?
CN, they go together.
What's the charge on it?
Minus.
Correct. Okay.
All right.
I think we'll call this one the last one. Decide whether the following are water soluble.
Well, it's a halide that's not mixed with any of the three. So A, I would say is.
Correct. How about B?
It's a nitrate, so yes.
Yep. How about C?
Yeah.
Yes, because the nitrate. Nitrates don't have any exceptions.
And then the sulfate is because it's with barium.
Is what?
Soluble?
No, sulfates are soluble generally,
Okay.
unless with barium or strontium or lead 2 and so forth and so on.
Okay.
So sulfates are generally soluble, and you have to try and remember the exceptions. Barium sulfate is not water soluble.
Okay. And
Okay.
those are all things that we should definitely memorize.
Yeah. You should try to memorize the solubility rules that I gave you, because when you're doing problems like this, especially on a test, you don't want to have to refer to a chart and figure it out.
Right.
Let's take a look at this one. So you did ask at the beginning of the session, how do you balance these and write net ionic equations? So let's take a look at this. So this happens to be a precipitation reaction. And here, that means that all of this is occurring in water. So let's write out the formulas for these and add the appropriate label. So if it's a solid, you write S. If it's a liquid, you write L. If it's a gas, you write G. If it's dissolved in water, you write AQ. So would this be dissolved in water?
Yeah, because of the nitrate.
Excellent.
Aqueous.
How about the Na2CO3? Would that be dissolved in water?
Yes, it's aqueous because of 1A ion.
That's right, because the sodium ion. Would this be dissolved in water?
Well, it's a carbonate, so no.
So no. So what do we put behind it?
Solid.
Solid. And would this be dissolved in water?
Yeah, because it's a nitrate.
Okay.
It's aqueous still.
Now, this is the reaction that they ask for, but we need to balance it. How many nickels?
1 and
How many
1.
nickels?
1 and 1.
How many nitrates on the left?
2.
How many on the right?
1.
How do you fix it?
Put a 2 in front of the products.
Okay. Now, when I put the 2 there, does that affect anything like the nickel that we've already counted?
It affects sodium, but there's already 2 sodium on the other side.
Okay, so now let's go to sodiums. We've got 2 and 2. How many carbonates?
1.
How many carbonates here on the right?
1.
1, right?
Right.
So we're balanced. Now, to write the net ionic for a precipitation reaction, you start with the solid. That's how you start. Okay?
Okay.
So what you put on this side? Well, you put down the 2 ions that make this. One of them was nickel and the other one was carbonate. What's the charge on a carbonate?
-2.
-2. And that was an aqueous ion that we got from here. So do you see that?
Right. They
Now,
should be aqueous, basically.
what's the charge on the nickel ion?
2 plus then.
2 plus. And it's aqueous that we got from here.
Okay.
So that's how you do the net. Start with the solid, then figure out what the ions were. They were
And
aqueous.
charge,
Pardon me?
you want the charges on the reactant side?
Absolutely.
Okay.
And if you want to write out the, not the net ionic, but the total ionic, you would take this and you would write nickel 2 plus aqueous plus 2 nitrates aqueous plus 2 sodiums aqueous plus 1 carbonate aqueous. And I'm going to give you a chance to catch up. But do you see how I took these apart and I wrote each ion separately
Right. With its own coefficient.
with its own coefficient based on how many of those ions there are.
Right.
And that's how you start. And then over here, notice this side. For the solid, I don't write them separately. And the reason I don't is because they are ionically bonded together. Here, they're free floating in solution. They're not bonded together. Here, they're not free floating in solution. They are bonded together. And then what am I going to do for the 2Na-NO3?
Well, they're still in ionic form.
So I'm going to write 2Na plus aqueous plus 2NO3 aqueous. Okay. So
Okay.
take a look here. I'm going to underline some things. This guy and this guy and this guy and this guy. Do you see how we start off with 2 nitrates that are dissolved and we end up with 2 nitrates are dissolved?
Right.
And we start off with 2 sodiums that are dissolved and end up with 2 sodiums that are dissolved.
Right.
So what has happened to those if they're the same before and after? And the answer is nothing.
Those are what you call the spectator ions.
This is a spectator ion.
Okay.
Now, can you see how these 2 ions, which I'm going to put a little thing like that underneath, these 2 ions, which were free floating, are now ionically bonded together.
Right.
So the formula has changed. This is a chemical reaction and they belong in the net ionic. So the net ionic is basically what really happens. And this total ionic, we could call it the gross ionic. Do you know the difference between gross and net?
Yeah.
What's that?
Yeah.
Okay. So we could call it the gross ionic equation, but I like total ionic better.
Mm-hmm.
So that's what's happening here.
Awesome.
And I think we'll end there. You did ask how to balance these, and you'll notice that we can balance by ions, not necessarily by atoms.
Right.
So I didn't have to do nitrogen, nitrogen. I could say actually nitrate, nitrate.
Right.
Okay.
Awesome. Thank you.
You're welcome. We'll see you tomorrow, I hope. Bye-bye.
Have a good day. Bye.